Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. Welcome to the Primary Loop. I'm Jim Anderton, Multimedia Content Director here at Engineering.com. Microscopy has been the key to understanding everything from the nature of disease to the behavior of metal alloys, and it's used everywhere from medicine to manufacturing quality control. Optical microscopy has resolution limits that are strictly dictated by the physics of light, and even electron microscopy struggles at atomic scales. But there's another form called atomic force microscopy, which can reach down to the atomic level and deliver insights that have broad applications in science and engineering. Atomic force microscopes are traditionally expensive research tools, but a new generation of machines promises to bring them within reach of scientific and industrial users everywhere. Joining me to explain how is David Morris, Director of Operations for Waterloo, Ontario-based ICSPI. Dave, welcome to the Primary Loop.
Thanks so much for having me, Jim.
Dave, to start, just can you define, please, what is atomic force microscopy?
Sure. So atomic force microscopy, or AFM, is a type of microscope that doesn't use any lenses. So unlike optical microscopy or SEM, like you mentioned, it's a physical type of microscope that works a lot like a record player. So we have a sharp stylus that moves over the surface of the sample, and it collects the 3D topography data of that surface. And so close that we're detecting the intermolecular forces between the sample and the probe. And it does that at extremely high resolution.
What are you doing that's different in this case? I understand you've shrunk this thing down to sort of a chip scale.
That's right. So I think a good analogy is something like, how in the 40s and 50s you had the ENIAC, the computer took up the size of a room, and today, we have more compute power in our pocket on a chip. And it's a similar thing where, a typical AFM is the size of an industrial oven. And so what we've done is taken the components of an AFM, which we can talk about, and integrated those onto a single chip using what's called MEMS, micro electromechanical systems. And so what's a little bit different with that is, since we've integrated everything onto a chip, it actually dramatically simplifies the operation and speeds things up. So instead of it being a super finicky technique like you were talking about, mostly relegated to, used by a PhD in a physics lab, we're able to, broaden that a little bit, and so that it's used in manufacturing environments.
Now, those of us who've worked with scanning electron microscopes, and I'm one of the fortunate few that can say that, know that sample preparation is everything. What's the sample preparation like to use your process?
Yeah, great question. So typically you can image most things just by placing them on the sample platform. As long as they fit, you can scan, the surface. When something is extremely rough, there's limits to how much the probe can go. We're usually talking about probing at the kind of nanoscale up to the micron scale. So if it's an extremely rough surface, that's not going to work so well. But if you have, say, like a piece of steel, an optic, something on a glass slide, like a biological sample, you can just place that, and then the probe can scan across it. So as long as it's a physically solid sample. There are also AFMs that operate in liquid, but that's more for biology and life science.
Yeah. Now you've used words like nanoscale. We were talking about microscale. What is the resolution of this unit? You've talked about the sort of the binding forces between atoms here.
That's right. So AFMs have some of the highest resolution of any kind of microscope. We're talking about going down to, nanoscale or sub-nanoscale, even, so say sub-angstrom, which is just mind-bogglingly small. In our case, for our systems that use our MEMS technology, we're at about, say, 0.5 nanometer down to about 0.1 nanometer. So we can look at, say, the step heights of a lattice for a ceramic like silicon carbide.
What's the situation with your apparatus, basically? Do you need to have specialized training to use this, or is this the kind of thing that, say, a metallurgist or a material scientist could just grab and use?
Yeah, that's exactly right, Jim. That, in kind of traditional AFM systems and SEMs, like you're saying, usually you have to have a lot of training, and often, it's going to be a PhD level microscopist that will be using the tool, and they'll be the tool owner. And so, with our tools, they can be used on a benchtop by anyone. What the MEMS device does is really simplify operation, and so you're able to go from loading a sample to scanning in just a few minutes.
Dave, in the world that I know and love in manufacturing, we're interested often in things like metallurgy, grain boundaries, twinning, compositional effects, especially as things like metal alloys and cermets use vanishingly small quantities of dopants and things which are really interesting at the nanoscales. Do you see this tool as a research tool, a production sort of quality verification tool, a bit of both? Where does it fit in?
Yeah, so AFM definitely has a role to play in metallurgy and in manufacturing, not maybe so much in line, like on the manufacturing line, but definitely as a quality control tool. It is used a little bit, but because they are so complicated and historically have been complicated, they're not used as much. But as an example, let's say that you're doing metallography on a piece of metal. Using a metallographic microscope, you're not really able to resolve the scratches necessarily. And what AFM really shines at is getting that three-dimensional data. So you can look at the scratch patterns. You can get actual the height and depth information of those scratches. You can look at grain boundaries, and we can look at those really small components. So a key differentiator between AFM and, say, optical microscopy is also the lateral resolution. Because you're limited by light with optical, you're talking about hundreds of nanometers, whereas with AFM, because of the sharp probe, we are able to see small pockets of materials in an alloy, for example.
Is this the machine that you can sort of pop into an engineering development lab, R&D lab, or a quality control lab?
Yeah, it can be used on a regular benchtop. So we, with the MEMS, we're able to suppress building vibrations. So AFM is an extremely sensitive technique. You're like we were mentioning, you can sense intermolecular forces between the tip and the sample. So it is sensitive to, say, a train going by or building vibrations, an elevator. In our case, because the system's so small, the high resonant frequency of the system rejects those building vibrations. And so you can use it on a regular benchtop.
Yeah. Those of us that have prepared samples for metallography, of course, know that it's a laborious process of embedding a metal sample into a thermoplastic puck, and then it's like a series of finer and finer abrasives, finally coming to something in the end, and then an etchant. And the sense we always had was that when you're etching a grain boundary, you're widening that chasm, so you're inferring a behavior rather than looking at it directly. Do you think there's going to be a difference in the way, say, in this metallography example, engineers look at things like twinning or grain boundary behavior, looking at it directly rather than sort of dumping it in hydrofluoric acid?
Yeah, that's right. Yeah, quite possibly. So when you are, it opens up and expands kind of access to the nanoscale, and you're able to build structure property relationships with more resolution.
In the future, can you see a role for automated AFM?
Definitely. So, when it comes to industrial applications and industrial use of AFM, the big industry that uses it is the semiconductor industry, and it still really isn't used in line as a technique because it's still a bit too slow. You're scanning a really small area. I mean, typically up to about 100 by 100 microns, and the breadth of human hair is 100 micron. So you're not able to really scan across the entirety of the wafer. And it'd be the same type of thing for in kind of traditional manufacturing environments. But certainly, there are ways to, let's say that because the AFM is integrated onto a chip, if you're able to do multiple AFMs and scan with multiple chips at the same time, you can really boost the throughput and really make the data meaningful. There's definitely potential there.
Yeah. The death of Moore's Law has been predicted for a couple of decades now, because the belief being there's no way we can get these things smaller, because we're no longer sort of doping sort of macro scale quantities of silicon or germanium. Now we're talking about things on the atomic level. Is this kind of technology going to be the key to keeping Moore's Law going, do you think?
Great question. I mean, Certainly metrology, and so the science of measurement, those tools have to keep up with the manufacturing, right? Otherwise, you really, it was Lord Kelvin who said you can't make what you can't measure. And so it's true, and AFM can definitely play a role. The issue is keeping up with the speed and pace of manufacturing. And so bringing AFM to, inline quality control and inline metrology in semiconductor industry definitely could help in pushing Moore's Law and keeping it going for the decades to come.
Amazing. David Morris, ICSPI, thanks for joining me on The Primary Loop.
Thanks so much, Jim.
Well, that's it for this episode of The Primary Loop, brought to you by engineering.com. For our deeper engineering series, visit engineering.com TV for exclusive shows like Manufacturing the Future, Designing the Future, and the Engineering Roundtable, not found here on our YouTube channel. The links are in the description below. Thanks for watching.